B.2, efficiency analysis of binary search. So now, let us do this binary search first, because it's pretty simple. Yeah. After we use the elimination idea, it is straightforward. Yeah. We just run it. All right. But when we run it, we want to look at this number of comparisons for the worst case. For other cases, we look at later. Okay, yeah, the worst case first. Let me use this line to represent the whole array of the original data. Now we have our given key, V, to compare it with the median. Okay. Now you know the meaning of the median. Okay, yeah. After one comparison, how much size reduction, problem size reduction do we have? We drop 1/2 of the data, approximately 1/2 of the data. Yeah. All right, so that's one comparison. Now we do the second comparison. Okay, worst case, that means we need to keep going. Yeah. We will not stop in the middle. We will keep going all the way down to the last element. Okay, only one left, then we stop. Okay, that corresponds to the worst case. All right, so the second comparison, we drop 1/2 of the current problem size. Then we keep doing this every time we chop 1/2 of the data size. And after k comparisons, suppose we get data size as small as this one, k comparisons. So now we want to describe the number of comparisons and the number of problem size. What is the relationship? We want to see that. In order to estimate worst case efficiency, we need to have that kind of relationship. Yeah. So here I draw a table like this. When you do one comparison, you reduce the problem size n/2. 1/2. Yeah. So don't worry about integer division or not. Yeah. Just approximately. Yeah. So then two comparisons, the problem size n/4. Okay. K comparisons, the problem size n/2 to the kth power. That's simple. So that's straightforward. Yeah. Now we need to estimate what is the last comparison to get the final element left. We want to find that point. Yeah. So the question, at what time should we stop splitting? Yeah. Because when you reach the final element, you cannot stop it. You cannot split it anymore, right? You cannot split your current data size anymore. So we want to look at that critical point. Yeah. Yeah. All right. So now we do the observation, critical observation like this. Yeah. After the last comparison, the data size should be less than 1. Strictly less than 1. The data size here, we mean this expression, okay? So this expression, that is our data size expression, okay? Yeah. This expression should be less than 1. If not, if greater or equal to 1, think about it. We have an interval longer or equal to 1, at least 1, then there is a possibility it covers 2 elements, right? There is a possibility it can cover 2 elements. Okay, yeah. Yeah, because the distance between two elements, that is 1. But now your size is greater or equal to 1. So, you can cover, at least there is a possibility you cover at least 2 elements. There is a possibility. The possibility is not 0. Okay? So we should consider it. Yeah. But if the data size will require strictly less than 1, then there is no chance this data size you can cover 2 elements. There is 0 chance. So that's why this condition gives us absolute stop. No alternative. So it is an absolute stop. Okay? So that's what we need. Absolute stop. That's what we need. Okay? Now we want to look at this point. Yeah. All right. Let's consider this inequality. Yeah, the data size less than 1. Yeah, we need that. But we also need this half. That means the previous data size. Yeah, before it's split to get this size, the previous data size should be greater or equal to 1. Yeah. That's the precise description, right? So if we consider this situation, then that's the precise description. Okay? Not too big, not too small. Yeah. This K cannot be too big, too small. Yeah. Otherwise, you can just make this K really, really big, right? Yeah. The larger the K, the smaller the fraction n over 2 to the kth. Right? Yeah. It satisfies less than 1, always satisfies 1, but that's not what we need, right? So we need to add this half of the inequality so we control your K cannot go further larger, cannot. Yeah. All right, so that's important. Yeah. So this inequality is important to catch the critical point. Yeah. All right. Yeah. Next, we just do the math to simplify this inequality. Eliminate the denominator, so we get the equivalent inequality like that. Then we take log base 2, so we get this expression. Okay? Yeah, we get this expression. Yeah. All right. But the answer, number of comparisons for the worst case, this number should be integer, right? It cannot be, yeah, because for the general n, log base 2 of n, not necessarily an integer, right? So we have to take floor ceiling function to make it integer, right? But what is the precise answer? We need to know. So our next slide, we want to find that answer. Yeah. All right. So we want to derive. Currently, we already have this one. But from this inequality, can we derive the worst case formula? Yeah. Still, we need to do some work to get a precise formula for the worst case formula. Yeah. All right. So let's do some more work. When we start, so we change a little bit from this one, we can get that. We can get this inequality. Yeah. But here, be careful. Strictly less than K, less than or equal to K, that is important. The equal part is important. Okay? Yeah. So we need to be very careful on that. Okay. All right. All right. Let's just go back to the previous inequality. We derived this before. Yeah. So this is the one we used to generate this current inequality. Yeah. So, but we need to go back a little bit. Yeah, because it is still useful. it can help us to find some good property we need. Yeah. All right. When you look at this one, I like you to see this part, focus on this part, n less than 2 to the kth power. This one, okay? Yeah. What? Because this one is interesting. Yeah. N is an integer, right? N is an integer. 2 to the kth, also integer, another integer. One integer less than another integer. Okay? And it is strictly than. Not less than or equal, strictly than. So one integer strictly less than another integer. So what conclusion you can get? Okay? When we add 1 to n, what can we get? Yeah, because n is strictly than 2 to the kth. When we add 1 to this n, then can we say less than or equal to 2 to the kth? Yeah, so look at this. We just add 1 to n. Then we can change strictly less to less than or equal to. Yeah, the reason we do that, we can improve our estimation. Okay? Yeah, improve the estimation. Now we try to use n minus 1 compared with 2 to the k. So the gap is smaller than the gap between n and 2 to the k, right? So we reduce the gap. Then we improve the estimation. Okay? All right. So now we can get this new inequality. Yeah. Look at this part. We take log base 2, both sides. We get this part inequality. See? Both sides. We get this part. Then this part comes from here. Comes from here. How about that? Okay? Come from that. Okay? Yeah. So finally, we get a new inequality. This is inequality. Because this inequality, the nice thing is we have less than or equal, including the equal case. Including the equal case, then there is a possibility they are equal. So that means our approximation is pretty good. Containing the equal case, so the problem approximation is pretty good. Yeah, this case approximation is not good because we don't know how large is the gap. The gap could be huge, right? So we don't know. But if you include the equal case, then the gap could be 0, right? When they are equal, the gap is 0. Yeah, so that means this time the approximation is pretty good. Yeah. So we are very satisfied on this approximation. Next, conclusion, the formula. Yeah. 2 formulas. Yeah. From this inequality, we can derive 2 formulas. Yeah. One from the left-hand side, one from the right-hand side. 2 formulas. Right? From left-hand side, when we take the ceiling function, okay? Yeah. So that is the smallest k, right? Smallest k, the ceiling function of that log base 2 of n plus 1. Okay? That is our first expression. K max. The max corresponds to the worst case, right? Because worst case, you use the maximum number of comparisons. Yeah. Here, we use this K max. Refers to worst case number of comparisons. Yeah. K max equals ceiling function of log base 2 of n plus 1, the first formula. Second formula, floor function, right? From the right-hand side, floor function, going down. Okay? Yeah. And floor function, remember this integer 1, we can take it out of the floor function, right? Yeah, we have that property. Okay, we used that before. Yeah. So our second formula is K max equals 1 plus floor function of log base 2 of n. Okay? You see, both formula true. They have different forms, but they are equal. Now, they are equal. Yeah. So finally, we can get this formula. Okay, these two expressions looks different, but we can prove. So if you want to prove, we can prove it. Okay, you can use mathematical induction to prove it. Okay, yeah. It's a good exercise problem. All right. So, but the answer, we have the answer. So when you do the calculation, the worst case for the binary search, you can use either formula. Okay, anyone is correct. Either one. Okay, yeah. All right. So now, after this formula, that's the worst case. So let's look at all other cases, yeah, for the binary search. For the binary search, the best case is 1. If you are very lucky, the given key equals the median, then you're done. Yeah. Best case 1. Yeah. Worst case, this number. Okay? But next question, average case. What is the average case? Yeah, that's not easy. That's not easy. You need to do some work to get it. Okay? Yeah. But I want to ask you this question. Can we say the average case is just 1 plus, best case plus the worst case divided by 2? Can we? Only the median gives you the best case. All the remaining cases, you cannot get the best case. Yeah. So, the cases you get different number of comparisons, quite different. Okay. So the distribution is not that even, not even. So you cannot do a simple average like this. So it is wrong. Okay. Yeah. Yeah. All right. Our next question, how do we find it? How do we find average case? Okay, yeah. Let me ask this question. What is the average case efficiency? So our next step, we need to find the answer. Yeah. But to find the answer, here, I do not want to make it too complicated. Yeah. So at this point, I do not want to make the problem too complicated. So I only ask you one example for n equals 7. So I want to show you one example when n equals 7. So you get an idea how to find the average case efficiency. Okay, so my next slide, I will show you how to do it. Okay. All right, so let's solve this problem. Average case efficiency for n equals 7, the binary search. Yeah. All right, here, to do that, let me draw a diagram. So from this diagram, you can get the answer not very hard. Yeah, pretty straightforward. Yeah. All right. We have 7 elements sorted array. Yeah. So I like to draw in this way. Okay. So you can see these 7 elements are arranged clearly, so we can work on it. Okay. So we can draw some diagram figures to represent the situation. Yeah. So let's work on it. Binary search. Yeah. First, we compare with, so when we do comparison, this V, we assume it is in the array. for simplicity, okay? Because there is a chance the V may not be in the array, right? Yeah, there is possibility of that, okay? So if we consider more general case, we should assume the probability that V is in the array is P. Not in the array, not, okay? Not in the array, 1 minus P, okay? Remember what we did for the linear search. We assume that, right? Yeah, but here I want to make the question as easy as possible. I just assume this V, we know already in this array, okay? So you do not need to worry about V is not in the array, okay? Under this condition, we can draw a binary tree to get the answer. All right. First, we compare the key with median, element number 4. All right. So if we are lucky, V equals element 4, one comparison. Okay. So we put there 1 for element number 4. Okay. After that, the binary search, you may go to the left half or the right half if V is not equal to 4, right? If V is not equal to 4, when you move to the left, you need to compare it with element number 2. If you go to the right, you need to compare the element number 6 based on the binary search. Okay, yeah. And if V equals 2, element 2 or element 6, you need 2 comparisons. So we write number 2 comparison, that number, the same level. Yeah. Yeah. So we will use these numbers later. Yeah. After that, if it's not 2, not 6, you also go to the left, go to the right. So this time 1 or 3. Yeah. If it's not 6, yeah, but higher than 4, value of 4, you go to left, right, so 5 or 7. For this case, you need 3 comparisons. For all these 4 elements, you need 3 comparisons. So that's all the possible cases, right? We list all the possible cases. Now we are ready to find the average of all the cases. Now the average formula is this. Because we have 7 total cases, so the denominator must be 7. Then the numerator, we do this. One comparison, how many elements we need 1 comparison to get a hit, right? To find it. Yeah. That's 1. So 1 comparison, the number of elements is 1. Okay? 2 comparisons. 2 comparisons, the number of elements that correspond to 2 comparisons. That's 2. Okay? 3 comparisons, the number of elements that corresponds to 3 comparisons. That's 4. Okay? So that's why the numerator, you do the multiplication and addition. So 1 times 1 plus 2 times 2 plus 3 times 4. Okay. So the answer is 17/7. That's the way we find the average case efficiency for the binary search. Okay? Yeah. After you understand this method, yeah. Later, when I give you different n number, for example, I may give you n equals 10, right? Yeah. N equals 10, it's not a complete binary tree, yeah, but it is a binary tree. You can draw it, right? Can you find the average case efficiency? Right? Yeah. All right, so now I finish part B.2, and we finish the binary search topic. Yeah. Next video, we will start the fake coin problem. All right.